Hello, this is a simple lesson about simple harmonic motion, starting with a mass on a spring. If we consider this picture here, where there's a mass m attached to a spring with spring constant k, ignore any gravitational effects that might be happening. What we need to think about is what happens when you move this mass m by some amount x from its equilibrium position. And now what would happen is there would be a force coming from the spring. And according to Hooke's law, you can work out the force from the spring as F is equal to kx. And the important thing about this force for simple harmonic motion is that it acts in the opposite direction to the displacement x, which means it acts to restore the mass to its equilibrium position around here. This is important. So if we can write down the equation of motion for this system, we can work out how it moves over time, and then we will find out that it's got something called simple harmonic motion. And if we use Newton's second law, is more formally, informally say it as F is equal to ma. Now we can write this as mx double dot, which is going to make it a lot easier in the future to just work through all this stuff. We know that this force on this mass, the only thing that acts on it is the spring. We ignore gravity, which means we can equate mx double dot to minus kx. And then we can bring the kx to the other side, such that we have mx double dot plus kx is equal to 0. Now this is not in its simplest form yet, so we put x double dot, divide through by m, you have k over mx, we say that's equal to 0. The important distinction here is that now we set this k over m to omega, which, if you are familiar with omega, it's also equal to 2 pi times f, which is the frequency of oscillation. So we have omega here is equal to k over m, which means you can find out the frequency of this oscillation just from the spring constant and the mass. And to solve this further, you would need to find solutions for x that would solve this equation, and there should be something that comes to mind immediately. It's a function that when you derive it twice, it goes directly back to the original function, and that can be pretty much any sine or any cosine. And the one that you use typically is cosine, because you start your displacement at some value 1, for example, and then you put some phase shift in, just to account for any difference in starting point. These things are dependent on something called boundary conditions, which you can cover later. It just depends on how the mass starts moving, where it starts moving from. More interestingly, we can look at why this f is equal to minus kx here, why that would lead to simple harmonic motion. To do that, we need to consider the energy of the system. So we have E here. And the energy would look like a quadratic, because if you recall, for a spring, the energy is equal to half kx squared. So that's a quadratic. And at the start, your mass is here. It's at its bottom. It's at the equilibrium position. It's happy there, so it's not going to move. There's nothing causing the energy to go up. As soon as you displace it, this term is no longer 0, and your mass ends up around here in terms of energy. And what the force acts to do is to bring this down. So it's a restoring force. It has to put the energy back to equilibrium. And it's a really simple way of understanding why simple harmonic motion will occur in instances like this. If you want to work out the period of oscillation for a sub-harmonic oscillator, especially this one in this case, you already have that omega is equal to k over m is equal to 2 pi f. And now from here, you could just go straight into finding the periodicity. Oh, sorry. Oh, that's meant to be an omega squared, actually. Sorry, I misspoke. So this is all omega squared. And now rearranging from this, we have that root k over m is equal to 2 pi over t. And then rearranging, we have t is equal to 2 pi root k over m. And that is the period of oscillation for that spring. Now, the other example of a simple harmonic oscillator you're about to cover is a simple pendulum. And in this diagram, we have a simple pendulum set up. And one thing you should work out is what forces are acting on this pendulum. It is a light string or a light rod, no friction. The only thing is a point mass at the end with mass m, and it's got small amplitude oscillations, which means that theta is small, because you can consider the amplitude as a function of the arc covered by it, which depends on theta and L. So for this case, the main force you have is gravity. But gravity, this component of gravity, it's not the entirety of gravity that's going to restore this in this direction. So what acts as a restoring force in this situation? It is gravity, but it's the, if you do some similar triangles here, and look at these angles, you'll find that this is mg sine theta. Sorry about my handwriting, I'm using my mouse right now. So the restoring force is mg sine theta. Now, to immediately simplify this, you can simplify later if you need. The approximation here is that this is a small amplitude, which means that sine theta is approximately theta. Because if you look at the sine graph, at very small theta, which is around here, it's almost a straight line going up. So that looks like theta, essentially. So you can use that approximation, which means your restoring force is now going to be mg theta as opposed to mg sine theta. And then there's also another thing where instead of using ma for your Newton's second law, because you don't just have x direction acceleration here, you have it in theta. You have to work out what a would look like in theta. And in this case, because you're using the arc length, that would be m, l, the length of the rod, and then theta dot, double dot, for acceleration. And then once again, like before, you can equate this and the restoring force to give you your equation of motion for this system, which would be minus the, remember it's always minus because the force acts against the displacement. Displacement goes this way, and your force is acting that way. And then rearranging as follows, you get omega double dot, sorry, theta double dot is minus g over L theta equals 0. And you can compare this to the equation earlier, which was that x double dot minus k over m x is 0. And you can see that they're very similar. Every simple harmonic motion will have this. The coordinates that you have the acceleration in, and the displacement. And it's the same here. Here your coordinates x, here you have theta, and then you have normal theta, and then another normal x. So these things always have to be the same. You can relabel g over L and k over m as omega squared. And in both cases, it gives you the period of oscillation. It gives you the angular frequency in both cases. So omega squared is replaceable with both of these terms. And in this case, now instead of having k over m as your angular frequency, you have that equal to g over L. and you can work out the period of oscillation for this one, which should be 2 pi root g over L. Okay, that's a quick summary of two very simple harmonic oscillators. This concept comes up all over in physics. It comes up in quantum mechanics. It comes up in thermodynamics afterwards as well. It's a very important phenomenon to know. You will have to model it in 10, 20 different ways in the future. So it's very good to have a grasp of superharmonic motion. Thank you.